So for the second half of Chapter 8, Objective 8, we're going to be testing and finding our interval of convergence through the ratio test. So just a reminder on what your ratio test looks like. So that would be when we take the limit to infinity of the nth plus 1 term over the nth term. But remember, we'll always, multiply by that reciprocal. If that ratio is less than 1, then we have a converging series, right? So if we have that ratio less than 1, we have a converging series. Greater than 1 diverges, equal to 1 inconclusive. And that equals to 1 inconclusive part is what we're going to be using and evaluating our endpoints, because our endpoints will be when it's equal to 1. And so we won't be able to use a ratio test for that. We'll have to find the other ones. So the beginning part of these notes is just a review, like what we call a power series. It has that variable term in there of x. Our domain is the values that will allow that power series to converge. And then we have 3 instances of convergence. One is it will be a single value in the domain, and so it would only converge at the center. The second component will be when we have an interval of convergence with a finite radius. And then finally, our last situation would be if the series converges for all values of x, so our domain would be all real numbers, right? So those are the 3 instances, right? So we have a finite value of r. We have a situation where r is equal to 0, and then finally the last situation when we have an infinite value of r, meaning the domain would be all real numbers. All right, so our endpoint convergence, so this is only done when it is not geometric, which will be then we will use the ratio test. So if it is not geometric, we will use the ratio test. And if we use the ratio test, you must evaluate the endpoints of your interval of convergence using a different test. So ratio test won't work when we're at the ends of our radius, okay? All right, so if it is geometric, you do not need to test the endpoints. If it's ratio test, then you have to test the endpoints. And why is that? Because when you are at that equals 1 component, remember, for ratio test, the test is inconclusive. Okay, so here we go. So we are going to go ahead and write our steps here. For just, now this is general, so like I know we've already done geometric, but I'm still going to kind of reference that a little bit. So the first thing that we need to do is identify if this is geometric or not. And it is geometric if n is the only place for n is in the power. And so here, n is in the power, woohoo, n is in the power, still woohoo, n is not in the power, boo-hoo. So because n is not in the power, then we cannot do geometric, right? So is a power series geometric? So yes, if it is, then you're just going to set your ratio less than 1 and solve. If no, then you're going to use ratio test. And that's because it will work a whole lot easier than any of our other tests. So in this particular case, so here is our ratio test. So the first thing we're going to do for our ratio test is we're going to identify a sub n, and a sub n plus 1, just like we did when we first did it. So we're going to identify our nth term and our nth plus 1 term. So this is, if you need to, go back and review those ideas. So our nth term will be negative 1 to the n, x to the n all over n, right? So I'm just looking at that. And then my nth plus 1 term is everywhere that I see an n, I'm going to replace it with n plus 1. right? So everywhere there is an n, we're going to replace with n plus 1. And then my second step is my next step is I'm going to set up my limit. And so that will be the limit as we go to infinity, right, of the nth plus 1 divided by the nth. And then I'm always going to just multiply by the reciprocal, though. So I will have the limit as n goes to infinity of my nth plus 1 term, so this one here. And then I'm going to multiply by the reciprocal of my nth term. And then after we set that up, now we're going to evaluate the limit. And make a conclusion. And we'll go into greater detail on that conclusion piece here shortly. Okay, so I'm going to go ahead and shuffle, right? So this is not a step that we need to do. It's just going to be a step that I prefer to do so I can, organize things and talk about it a little bit easier. So I have my -1 to the n plus 1, and then I have my x to the n plus 1, and then times n, right? So I'm just across the top. And then my denominator, I'm going to put my -1 to the n first, and then my x to the n, and then finally the n plus 1. And then we're just going to do a little bit of simplifying. So because we're taking the absolute value, if I were to subtract these powers, I would get -1 to the first, which would just still be -1, but because it's an absolute value, it's just going to turn into 1. So essentially, this is just going to be 1, so I don't need to have that piece of it. And then here I'm going to subtract my powers on my x terms. So x to the n plus 1, and then minus x to the n. So that would be, or n plus 1 minus n, so that would be x to the first, right? And then I still have times n, and then over n plus 1. So now what I'm going to look at here is my variable that I'm working with is n, right? So n is approaching infinity, so that's what I'm taking the limit of. So this piece right here, I'm not taking the limit of. And so because of that, I can pull that out to the front, right? Because it's not a variable of n. But when I do pull it out, I need to make sure that I leave it in the absolute value. So that x to the first is going to go out to the front. But my n and n plus 1 needs to stay, right? Because I need to take the limit of that. So because these are of equal degree, then this is going to be a coefficient, looking at the coefficient. So that would be 1 over 1. So this limit will just go to 1, but remember it's being multiplied by the absolute value of x. So that would be the absolute value of x. All right, so now here's that make a conclusion component. So on that make a conclusion component, what I have to recognize is that I am doing the ratio test. So the conclusion is that the value of the limit needs to be less than 1 to converge, right? And then if the value, and then equal to 1 is inconclusive. So what was the value of the limit? Well, the value of this whole limit process was the absolute value of x times 1. So that would be this piece right here, right? So that is the result of this limit. So the result of this limit is that. And I know by using the ratio test, if the result of the limit is less than 1, it's going to converge. So then my step 5 is to take the limit and set up the inequality. So the limit, and I'm going to put that in absolute value, needs to be less than 1. So then I will take the result of the limit, which is the absolute value of x, and make it less than 1. And so once I do that, now I'm going to use the tools that I learned last time to find my center, my radius, and my interval of convergence. Okay? So then now we're going to use the whole idea of the x minus c is less than r to find the IOC. So when I look at this, I know my center is 0 because I just have what am I subtracting from x, so that would be 0. My radius of convergence is right there, so that would be equal to 1, right? And so then now what I have is I'm centered at 0, and I can go out 1 to the right, so 0 plus 1, and 1 to the left, so 0 minus 1 puts me at negative 1. So then my temporary, so this is a temporary, IOC is from negative 1 to 1. So now what if the radius was 1? I mean, not the radius. What if the value of x was 1? So if I were to substitute in 1 here, I would get the absolute value of 1, which is 1. Then that would be inconclusive. So now I have to have this added step. So my step 7 is to test the endpoints. And that means you are going to substitute in x equals negative 1 and x equals 1 into the original power series and determine convergence. Okay, so what we don't know is, does x equal negative 1 converge or diverge? Does x equal 1 converge or diverge? Are they within the domain of the power series, meaning it will converge, right? So we're going to do 2 twice, right? So we have to test x equals negative 1. So we're going to let x equal negative 1. And we're also going to let x is equal to 1. So I have to go back to that original series. So let me zoom out just a tiny bit here, or maybe a whole lot. Okay, so we're going to take that original series, so this one right here, and I'm going to replace this x with negative 1 and positive 1. So for my first one, so I have negative 1 to the n, and now replace x with negative 1, also to the power of n, and then all divided by n. And then let me zoom back in a little bit. And then now I'm going to simplify this, and so I can test for convergence or divergence. So right here I have negative 1 to the n times negative 1 to the n, so I'm going to simplify that a little bit. So that would be negative 1 to the 2n all over n. And so negative 1 squared is positive 1, and then positive 1 to the n is positive 1. And so now I want to go back and review that 8.2 and 8.6. I know that this is a p series, and my power is 1, so it will diverge. So then that means x cannot equal negative 1, right? So that gives me a diverging series. So if you don't remember your rules, you need to go back and revisit those. So now I'm going to do the same exact thing again here. So I'm going to replace x with 1. So I'm using that original series, but replacing x with 1. So 1 to the n is just 1, right? 1 squared, 1 cubed, 1 to the 4th. And so then I have negative 1 to the power of n all over n. So this is not a p series, but an alternating p-series. So if it's an alternating p-series, I'm going to do the alternating series test. So an is 1 over n. So the first thing I want to do is take the limit to infinity of 1 over n, which is 0. So far, so good. And then I want to compare the nth plus 1 term with the nth term. So bigger denominator, smaller fraction. So it is decreasing. Excellent. Okay, so then that means x can equal 1 because I get a converging series, right? Alternating p-series converges. So then I need to adjust the domain here. So that means x can equal 1. So then I'm going to bracket that off. So that means I can choose any value between -1 and 1, not -1, but I could choose x equals 1. Any number in between there, substitute it into this equation, and I would get a converging series. Okay, so let's take a look at another one. Okay, so the first thing I want to do is recognize that this is not geometric, right? Because I have this in here. So then what I need to do is find my nth term and my nth plus 1 term. So I'm going to do that actually below here. So the nth term, and then replace my n's with n plus 1. And then once I do that, I'm going to go ahead and set up my limit. So I'm going to take those, and I'm going to find the limit of the nth plus 1 term. And then I'm going to go ahead and distribute in that too right now. And then I'm going to multiply by the reciprocal of my nth term. Get that absolute value in there. Okay, so I just set up the ratio test, and I have to do ratio test because it is not geometric, right? Not geometric. So then let's go ahead, and I'm going to do a little shuffling, get everything lined up. So I will have my numerator combined as one term. And then my denominator, so I'm going to put this first so it's aligned with the other 3x to the n. And then now for my factorial, I'm going to go ahead and count down because I can see that 2n plus 2 is bigger. So I'll have 2n plus 2. One term less will be 2n plus 1. One term left will be 2n, which aligns. So then I'll go ahead and slap a factorial on there. And then let's go ahead and do a little reducing. So I'm going to subtract my powers. So that would be 3x to the n plus 1 minus n. So that would be 3x to the power of n. And then here the 2n factorials reduce. Oh, wait, that's not true. Let me erase that. How about 3x to the power of 1? So n plus 1 minus n is 1. So then I'll have in my denominator 2n plus 2 times 2n plus 1. And then I see that I am taking the limit of n as n approaches infinity. There's no n here at all. So that means that can go to the front as a coefficient. And it's going to stay in the absolute value, right? So I'll be left with 1 in the numerator. And then if I distribute that denominator, not that I have to, like I can certainly leave that not distributed, but I'm going to go ahead and distribute that. So then when I go to take this limit to infinity, the denominator is growing to infinity while the numerator is staying constant. So that means the bigger the denominator, the smaller the fraction. So then this whole limit is actually going to approach 0. And so I would have the absolute value of 3x times 0, which is just equal to 0. So what is happening here then, again, so remember I'm using ratio test. So if that limit is less than 1, the series converges. So is 0 less than 1? And that would be yes, right? So that means that my series that I have converges for all values of x. And so the radius of convergence is going to be infinity, and then the interval of convergence is just going to be negative infinity to infinity, or all real numbers. And that's because that x term here is being multiplied by 0, which is going to be 0. So we don't have to solve for anything. All right. Okay, let's take a look at the next piece. So this is integrals and derivatives. And I just realized I was going to change the directions on this, and I didn't get around to that. So I will just change it here. So for this here, what I want to do is I want to find not the interval of convergence. I was copying and pasting. I want to find f prime of x, and then the integral of f of x dx in power series form. Okay, so fix those directions, but let's go ahead and talk about these properties here so we can see this. Okay, so for our properties, so we know that we are given a function that, so this is our power series function, right? So we have an and then x minus c to the n, and c being my center. If it has a radius of convergence that is greater than 0, then on the interval, c minus r to c plus r, right? So that's my interval of convergence, right? So that's what we've looked at already. And f is differentiable, and so therefore continuous. Then the derivative and the antiderivative are given in this fashion. So this is just doing power rule, where we take the power of n, right? So the power of n, and we move it to the front, and then reduce the power by 1. So that n moved to the front, and the power was reduced by 1. So this is a power series format. This is what we call term by term. Meaning here, if I took the derivative of a sub 0, that's a constant, so that would be equal to 0. So that's why there is no a0 here, right? Because that would turn into 0. And then here, if I took this derivative, I would have 1 times a to the first, which is a to the first. And then reduce the power by 1 would turn to 0, and that's why there's no x minus c here. And then here, pull down the 2, so I would have 2a sub 2, and then reduce the power by 1, power of 1, and then so on and so on. So this is our power series and format, right, where there's the derivative, and then this is term by term. And then integration works exactly the same, but we're using power rule where we add 1 and divide by the new power, right? So integration, same exact idea. So if I were to try to integrate this, I would add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power, and so on. So what does that look like? So we have add 1 to the power and divide by the new power. Okay, so that is derivatives and integrals. So sometimes people make it a lot more complicated looking than it really is. So just remember, we're just doing power rule for derivatives and integrals. So one thing though that we do need to take note of is that the radius of the radius of convergence of the series obtained by either taking the derivative or the integral has to be the same as the original power series. Okay, so for example, if the radius of convergence up here was 2, it would have to also be 2 down here. However, the IOC might be different based upon the endpoints. So it's possible that maybe up here the IOC was from, I don't know, -2 to 2. Then down here, it's possible that maybe the IOC was -2 to 2. You know, maybe differentiating eliminates one of those endpoints from actually working. Okay, so that's what they're suggesting. Okay, so let's go ahead and take a look at finding the derivative and the integral. And we're not going to do term by term, we're going to do it in the power series format. So the first thing I would do is rewrite it so that you can see what it is that you're actually taking the derivative of. This is not like a required step. It's just for you to see what you're looking at. So when I say rewrite it, you're going to put all your non-x terms first and then your x terms last. Like that's like kind of what you're searching for. So for this here, so I'm going to set up, so f of x. So I have -1 to the n plus 1, and then all over n plus 1, right? And then times x minus 1 to the n plus 1. So the only thing, so I'm going to find the derivative with respect to x. So I'm going to find f prime of x. So the only piece I'm taking the derivative of is this right here, right? Because that's the only piece that even has an x involved. So just to make sure we understand that component, if I were to tell you f of x was 3x squared, you're not touching the 3, right? So you're going to be looking at this as 3 and then multiplying that by the derivative of x squared. So f prime of x is still 3 times, and then the derivative here, you're going to do power rule just on that piece, which is 2x to the power of 1. So this coefficient never changes, right? I know that we multiply the 3 and the 2 together, but we're not taking the derivative of 3, we're taking the derivative of x squared because that's the x piece of it. And so I have to think of this as like the 3, that is just a coefficient, and then this is what I need to find f prime of. So I'm going to find f prime of just the x portion. So the coefficient is going to stay the same, and then I'm going to apply power rule for this piece. So I'm going to bring down the power of n plus 1, keep the x minus 1 the same, right? And then reduce the power by 1. So n plus 1 minus 1 would just be n. And then multiply by the derivative, because the chain rule of x minus 1, which is just 1. And so then the, oops, I meant to do this right now. So then the n plus 1s reduce. And so I was getting ahead of myself. And so the n plus 1s reduce, and then I don't need the times 1. So I would have -1 to the n plus 1, and then times x minus 1 to the power of n. So one thing I have to be careful of is I need to make sure that n can still equal 0. And so here, if I were to let n equal 0, do I get a non-negative integer power? And so if n were 0, that is fine. So n can continue to stay at 0. So let's do a what if situation so that makes a little bit more sense. So just off to the side here. So let's say that when I went to go take the derivative, so whatever the derivative happened to be, so let's say it was -1 to the n, x minus 2 to the n minus 1. Could n be equal to 0? Like that's what I'm asking, and still generate a polynomial. So if n were 0, I would get 0 minus 1, so that's a -1 power. Can that happen? Like, can you have a -1 power and still have a polynomial? And the answer to that question is no. So then if it did start at 0, it can no longer start at 0. It would now have to start at 1. So I would just increase it by 1 unit. So I would increase it by 1 unit, and then I should get a non-negative integer power. Okay, so that's what we do have, that extra check that we have to test when we're doing our derivatives. Okay, so there's our derivative. So now we're going to go ahead and find our integral. So let's find that integral next. So we'll do the integral of f of x. And so again, all we're taking the integral of is the x term. So that means we're going to leave the coefficient alone, which is what's clouded in red. And then we're going to add 1 to the power, so n plus 1 plus 1, so n plus 2, and then divide by the new power. And then because we're increasing our power, we don't need to worry about n being 0. Like that, of course, will keep with an integer power. And nothing reduces or simplifies, and so that would be my integral. And that's it.